Oh, those cancel, don't they? Minus mu g. Sorry, algebra. Huh. Cool. Huh. I forgot it simplified like that. Neat. If mu equals to 0, you're back to our previous result. It's a good sign. I'm going to do a really simple example next that illustrates why the normal force is not always just gravity. If I have a box like this, all right, and I've been doing a lot of pushing. Let me do a pull. And I pull on it like this, right? And let's suppose I pull on it with a force of mg over 2 at an angle of theta equals 60 degrees. All right, so I've got some, I guess you guys probably want me to put specific numbers in, huh? Fine, 30 newtons. And this is a m equals 100 kilogram box. And the coefficient of it's moving, and the coefficient of kinetic friction is 0.1. All right. The question then, of course, is what's the acceleration? Acceleration of the box. Hopefully I've made these numbers reasonable so that it wouldn't be like lifting the box up or something. We don't really have the analysis for that in here at the moment. The problem of like refrigerators tipping over, things like that, that's really a problem for the statics course. So you guys will take that, some of you. Okay, so here we go. We've got the normal force like that. We've got mg like that. And we've got the force of friction like so. But now, the fun part is that this force has to be broken into components, right? So you got 30 newtons, but there's a horizontal piece and there's a vertical piece. And what are those? Yeah, 30 newtons times the cosine of 60 for the horizontal piece, and 30 newtons times the sine of 60 for the vertical piece. So this is, the horizontal piece is 15 newtons, and the other one is whatever that is, 0.866 times 30, something like that, cosine, no, sine, sorry. 15 root 3. Yeah, thanks. No. 20, 25.98, right? Okay, so we look at the mass times the x acceleration, and we look at the mass times the y acceleration. Mass times the x acceleration is equal to what? It's equal to 15 newtons. That's the pulling force, right? Minus what? Minus the force of friction. Which, of course, I could write instead as what? 0.1 times what? The normal force, right? That's how friction works. That's an experimentally determined fact. I don't know if it's an experimentally determined fact as much as it is a tabulation of experimental results, but I don't know, whatever. Potato, whatever. MAY is what? I'm assuming that's 0. I'm assuming we're not lifting the box off of the plane. It's just sliding along, all right? So this is assumed to be 0, but what else is it equal to? Normal force, right? Minus mg, right? But now there's a new player. There's someone else involved in the vertical direction. This one. That interferes with the naive simplicity of the last example. And I'm sorry about this. Tell you what. There, better. Okay. So what's the normal force? The normal force in this case is mg. Oh, I'm sorry. Should this be minus? That should be plus, right? Thank you, guys. So minus 25.98, which is what? This is, what was my mass? 100 kilograms. So that's 980 newtons minus 25.98. It's going to be hard to tell the difference in this case. It doesn't change it much. Bless you. Stupid fraction. 954.02 newtons. So what we have then is that mass times the acceleration is equal to 15 minus 0.1 times 954.02 newtons. In other words, the acceleration is equal to 15 minus 95.402 divided by 100 meters per second squared. In this case, the acceleration would be if I didn't make a mistake, about 0.8 meters per second squared. Unfortunately, in this case, if you did this one wrong, you might still get it right because the adjustment from n equals mg to what it really is here is pretty slight, you know? If this was a WebAssign problem, if the tolerance wasn't set real tight, it might trick you into thinking you knew what you were doing when you didn't. If you always just say n equals mg, I'm sorry, but you're wrong. It's just not the case. You have to look at the sum of the forces in the normal direction to figure out what the normal force is as it relates to the gravity force. Okay? I hope I've given you an indication why we cannot neglect this detail. Any question?
It's negative, right, for acceleration?
Yeah, I got a minus.
Wouldn't it be AX?
I must have made a algebra mistake here somewhere. Oh. Oh, no, no, no. Ow, phooey. You see the problem here? My problem is unphysical. That force is not large enough to pull such a box. This doesn't mean much. I'm sorry. The analysis is still right, but it would be better if I had done something like this is 2 kilograms and then gone through it. This would have stayed the same, right? What would it have changed? If I changed that to a 2, all that changed it. mg is now what? 18 newtons.
Yeah, 19.6.
Oh, see, now I got too carried away in the other direction. Look, now it won't stay on the ground. I think. Now it's lifting up. That's too small. I'm facing the Goldilocks problem. This one's too big, that one's too small. Anyway. Fine, stupid Goldilocks. Hate you. 5 maybe? How's 5 sound? 5 times 9.8 is what?
49 something.
Yay! 49 point something. I'll use an S. I'm saying it's 49. All right, so is that right? Wait a minute, 5. Yeah, 49 newtons. Sorry. And then what's the difference here?
23.
All right. So that's the normal force. And now we got it. So that's 15 minus what? 2.302 divided by the mass, which we said was 5. And then that gives me what? Man, I had another interesting example I was going to show you guys, and we just wasted time on this nonsense. .54 meters per second squared. There you go. Yeah, it is possible to make up problems that don't make sense. Now, fortunately, usually your job is to solve problems, not to make them up, so you're probably okay. Although you should be worried about my ability to make up problems. That is true. Our next problem is to solve this problem. You take the box and you put it on the dreaded inclined plane. It has angle theta, and the question is, if this is a frictionless plane, what's the acceleration? Now it's fun. You see, the free body diagram is more interesting now. You have gravity like this, right?
Normal force is perpendicular.
Right, normal force like this. And if it stays on the plane, you see gravity decomposes into two pieces. This piece and this piece. Now, it turns out by geometry that this is actually mg cosine theta, and this guy is mg sine theta. And so the acceleration down the plane is equal to ma is equal to mg sine theta. And then on the other hand, if it's, the perpendicular direction gives us that the normal force is equal to mg cosine theta. And you can check special cases to see that that makes sense. Like if you put theta equals to 0, nothing happens, right? It's just a box sitting on a plane, right? And the normal force is what? Theta equal to 0. Normal force, mg. Very good, right? What happens if theta is 90 degrees? You get free fall, right? You get ma is equal to mg, and the normal force is what? 0. So these are the two extremes, sitting on the plane and then not sitting on the plane, just free falling. And everything in between that is interesting, and this is the inclined plane problem. Next time we'll study this, we'll add friction to it and study various questions about that problem. So thanks, guys.